we'll do a /marker. Start us off. We are ready to go. Okay, so event queue. This is chapter 15, I believe, of the Game Programming Patterns book. Let's just get into it. So, intent. Decouple when a message or event is sent from when it is processed. Right. So in a previous observer pattern, we created like an event system. And as soon as you run it, that's as soon as it runs. So it sounds like this is going to like be even one more step removed. Motivation. Unless you live under one of the few rocks that still lack internet access, you've probably already heard of an event queue. If not, maybe message queue or event loop or message pump rings a bell. Not message pump, I haven't heard of that one. The other ones I have. To refresh your memory, let's walk through a couple of common manifestations of the pattern. I successfully already turned off the tagging game. Cool. For most of the chapter, I use event and message interchangeably. Where the distinction matters, I'll make it obvious. Gui Event Loops. If you've ever done any user interface programming, then you're well acquainted with events. Every time the user interacts with your program, clicks a button, pulls down a menu, or presses a key, the operating system generates an event. It throws this object at your app, and your job is to grab it and hook it up to some interesting behavior. This application style is so common, it's considered a paradigm, event-driven programming. In order to receive these missives, somewhere deep in the bowels of your code is an event loop. It looks roughly like this. Okay, so while we're running, so get the next event, we have an event, and then handle the event. The call to get next event pulls a bit of unprocessed user input into your app. You route it into an event handler, and like magic, your application comes to life. The interesting part is that the application pulls in the event when it wants it. The operating system doesn't just immediately jump to some code in your app when the user pokes a peripheral. In contrast, interrupts from the operating system do work like that. When an interrupt happens, the OS stops whatever your app was doing and forces it to jump to an interrupt handler. This abruptness is why interrupts are so hard to work with. Like Control-C is a great interrupt. That means that when a user input comes in, it needs to go somewhere so that the operating system doesn't lose it. Between when the device driver reported the input and when your app gets around to calling get next event. That somewhere is a queue. Yeah, okay, so we have this operating system and here's our queue, which is like, okay, click, up, down, shift. And then get next event just pops off the latest one. When user input comes in, the operating system adds it to a queue of unprocessed events. When you call get next event, that pulls the oldest event off the queue and hands it to your application. Central event bus. Most games aren't event driven like this, but it is common for a game to have its own event queue as the backbone of its nervous system. You often hear central, global, or main used to describe it. It's used for high-level communication between game systems that want to stay decoupled. If you want to know why they aren't event-driven, crack open the game loop chapter. Say your game has a tutorial system to display help boxes after specific in-game events. For example, the first time a player vanquishes a foul beastie, you want to show a little balloon that says, press X to grab the loot. Tutorial systems are a pain to implement gracefully, and most players will spend only a fraction of their time using in-game help. So it feels like they aren't worth the effort. But the fraction where they are using a tutorial can be invaluable to easing the player into your game. Your gameplay and combat code are likely complex enough as it is. The last thing you want to do is add a bunch of stuff that checks for triggering tutorials in there. Instead, you could have a central event queue. Any game system can send to it, so the combat code can add an enemy died event every time you slay a foe. Likewise, any game system can receive events from the queue. The tutorial engine registers itself with the queue and indicates that it wants to receive enemy died events. This way, knowledge of an enemy dying makes its way from the combat system over to the tutorial engine without the two being directly aware of each other. Like the observer method also sounds like very similar to that, where they don't actually aware of each other and they're just getting these events. This model where you have a shared space that entities can post information to and get notified by is similar to Blackboard systems in the AI field. I'm not familiar with Blackboard systems, but I'm also not familiar with AI, like very much AI. So we have combat, like those are generating events, tutorials generate events, but they're also pulling from events, or pulling from the queue, which are the events. I thought about using this as the example for the rest of the chapter, but I'm not generally a big fan of big global systems. Event queues don't have to be for communicating across the entire game engine. They can be just as useful within a single class or domain. Say what? So instead, let's add sound to our game. Humans are mainly visual animals, but hearing is deeply connected to our emotions and our sense of physical space. The right simulated echo can make a black screen feel like an enormous cavern, and a well-timed violin adiago can make your heartstrings hum in sympathetic resonance. To get our game wound for sound, we'll start with the simplest possible approach and see how it goes. We'll add a little audio engine that has an API for playing a sound given an identifier and a volume. While they almost always shy away from the singleton pattern, this is one of the places where it may fit because the machine likely only has one set of speakers. I'm taking a simpler approach and just making the method static. Okay, so we have class audio, and then we're gonna have a play sound in it. And it sounds like we're gonna get into code here, so I'm gonna start adding in. So we're gonna start with JavaScript as our what we're implementing this in. And at the end of this chapter, if we feel that this is a good resource to sort of like play around with Rust too, we'll do that, but that's usually like the next day, which would be tomorrow. So we'll do class audio. And then this is gonna have a method on it called play sound that's gonna take the ID of the sound and the volume. It's responsible for loading the appropriate sound resource, finding an available channel to play it on, and starting it up. This chapter isn't about some platform's real audio API, so I'll conjure one up that we can presume is implemented elsewhere. Using it, we write our method like so. Okay, so here's our play sound, takes in ID and volume, and we need to like find the open channel. If the channel is -1, so if we don't have sound, return, just return, start sound. Okay, and then we could just call like start sound. So if I wanted like to pretend that this is like something that's runnable, we could have a function find open channel. We can just return 1. We found channel 1. And then we have here, okay, so const channel equals find open channel. I don't know, like that find open channel reminds me of like those really old games that I played where you'd have to like set up all those audio settings before you could play anything. And if you like chose the wrong one, there would be no sound, and you know that would just suck. And it was like all the Sound Blaster tools that we had to use. The memories. Okay, so if that was the good days. Oh man. If channel is equal to -1, then we just want to do an early return. And just sort of what he does here is fine. Like the same line, I'm a fan of that. Then we can just run start sound. So we'll have to have a start sound function, which takes in a resource, a channel, and a volume. Now, I missed this one. Resource, load sound from the ID. So we're also going to have no semicolon there. We do need that. And also function load sound takes in an ID. All right, so we're first gonna get const resource equals load sound, pass it in the ID, and then we're going to get this start sound, pass it in the resource, the channel, and the volume. All right, so that is our play sound. We check that in, create a few sound files, and start sprinkling play sound calls throughout our code base like some magical audio fairy. For example, in our UI code, we play a little bloop when the selected menu item changes. So we have our menu class. So we can have another class, menu here. We have an onSelect method that takes an index of what we clicked on. And then here we can just say, hey, audio, let's play, what am I doing with colon? That's Rust. Play sound. And then, well, so let's create some const sound bloop equals, let's just say 1. So we'll do sound bloop, and maybe we have volume max. Volume max equals 1. Volume X. After doing this, we notice that sometimes when you switch menu items, the whole screen freezes for a few frames. We've hit our first issue. Problem 1. The API blocks the caller until the audio engine has completely processed the request. Our play sound method is synchronous. It doesn't return back to the caller until bloops are coming out of the speakers. If a sound file has to be loaded from disk first, that may take a while. In the meantime, the rest of the game is frozen. Ignoring that for now, we move on. In the AI code, we add a call to let out a wail of anguish when an enemy takes damage from the player. Nothing warms a gamer's heart like inflicting simulated pain on a virtual living being. It works, but sometimes when the hero does a mighty attack, it hits 2 enemies in the exact same frame. That causes the game to play the wail sound twice simultaneously. If you know anything about audio, you know mixing multiple sounds together sums their waveforms. When those are the same waveform, it's the same as one sound played twice as loud. It's jarringly loud. I ran into this exact issue working on Henry Hatsworth and a Puzzling Adventure. My solution there is similar to what we'll cover here. We have a related problem in boss fights, when pals and minions are running around causing mayhem. The hardware can only play so many sounds at one time. When we go over that limit, sounds get ignored or cut off. To handle these issues, we need to look at the entire set of sound calls to aggregate and prioritize them. Unfortunately, our audio API handles each play sound call independently. It sees requests through a pinhole, one at a time. And when OSs were thin and every game shipped with its own tiny OS, there's so much that I'm like happy that we're not in there, and so much that like I miss from that time too. Problem 2, requests cannot be processed in aggregate. These problems seem like mere annoyances compared to the next issue that falls in our lap. By now, we've strewn play sound calls throughout the codebase in lots of different game systems. But our game engine is running on modern multi-core hardware. To take advantage of those cores, we distribute those systems on different threads. Rendering on one, AI on the other, etc. Since our API is synchronous, it runs on a caller's thread. When we call it from different game systems, we're hitting our API concurrently from multiple threads. Look at that sample code. See any thread synchronization? Me neither. This is particularly egregious because we intended to have a separate thread for audio. It's just sitting there, totally idle, while these other threads are busy stepping all over each other and breaking things. Problem 3. Requests are processed on the wrong thread. The common theme to these problems is that the audio engine interprets a call to play sound to mean drop everything and play the sound right now. Immediacy is the problem. Other game systems call play sound at their convenience, but not necessarily when it's convenient for the audio engine to handle that request. To fix that, we'll decouple receiving a request from processing it. The pattern. A queue stores a series of notifications or requests as first in, first out order. Sending a notification enqueues the request and returns. The request processor then processes items from the queue. At a later time, requests can be handled directly or routed to interested parties. This decouples the sender from the receiver both statically and in time. Okay, so I think that's the key, is the observer pattern only decouples statically. It doesn't decouple in time. When to use it? If you only want to decouple who receives a message from its sender, patterns like observer and command will take care of this with less complexity. You only need a queue when you want to decouple something in time. I mentioned this in nearly every chapter, but it's worth emphasizing. Complexity slows you down, so treat simplicity as a precious resource. I think of it in terms of pushing and pulling. You have some code A that wants another chunk B to do some work. The natural way for A to initiate that is by pushing the request to B. Meanwhile, the natural way for B to process that request is by pulling it in at a convenient time in its run cycle. When you have a push model on one end and a pull model on the other, you need a buffer between them. That's what a queue provides, that simpler decoupling patterns don't. Queues give control to the code that pulls from it. The receiver can delay processing aggregate requests or discard them entirely. But queues do this by taking control away from the sender. All the sender can do is throw a request on the queue and hope for the best. This makes queues a poor fit when the sender needs a response. Keep in mind, unlike some more modest patterns in this book, event queues are complex and tend to have a wide-reaching effect on the architecture of our games. That means you'll want to think hard about how or if you use one. A central event queue is a global variable. One common use of this pattern is for a sort of grand central station that all parts of the game can route messages through. It's a powerful piece of infrastructure, but powerful doesn't always mean good. It took a while, but most of us learned the hard way that global variables are bad. When you have a piece of state that any part of the program can poke at, all sorts of subtle interdependencies creep in. This pattern wraps that state in a nice little protocol, but it's still global, and with all the danger that entails. The state of the world can change under you. Say some AI code posts an entity died event to a queue when a virtual minion shuffles off its mortal coil. That event hangs out in a queue for who knows how many frames until it eventually works its way to the front and gets processed. Meanwhile, the experience system wants to track the heroine's body count and reward her for her grisly efficiency. It receives each entity died event and determines the kind of entity slain and the difficulty of the kill so it can dish out an appropriate reward. That requires various pieces of state in the world. we need the entity that died so we can see how tough it was. We may want to inspect its surroundings to see what other obstacles or minions were nearby. But if the event isn't received until later, that stuff may be gone. The entity may have been deallocated, and other nearby foes may have wandered off. When you receive an event, you have to be careful not to assume the current state of the world reflects how the world was when the event was raised. This means queued events tend to be more data heavy than events in synchronous systems. With the latter, the notification can say something happened, and the receiver can look around for the details. With a queue, those ephemeral details must be captured when the event is sent, so they can be used later. Like, enemy died, here's how much experience. Like, here's how many enemies were around it, or here's how much experience that enemy was worth. Or the ID of the enemy, so you can go look that up yourself. I guess it would be something like that. You can get stuck in feedback loops. All event and message systems have to worry about cycles. A sends an event. B receives it and responds by sending an event. That event happens to be one that A cares about, so it receives it. In response, it sends an event. Go to 2. Oh, a nice like infinite loop that we've created. When your messaging system is synchronous, you find cycles quickly. They overflow the stack and crash your game. With a queue, asynchrony unwinds the stack so the game may keep running even though spurious events are slashing back and forth in there. A common rule to avoid this is to avoid sending events from within the code that's handling one. Interesting, so you can have event handlers and event senders, but you want, I guess like one class, as it were, one object could do both, but like the function that does the sending should not also do the receiving. Or the pulling, I suppose. Although debugging logging your event system is probably a good idea too. Sample code. We've already seen some code. It's not perfect, but it has the right basic functionality, the public API we want, and the right low-level audio calls. All that's left for us to do now is fix its problems. The first is that our API blocks. When a piece of code plays a sound, it can't do anything else until playSound finishes loading the resource and actually starts making the speaker wiggle. We want to defer that work until later so that playSound can return quickly. To do that, we need to reify the sound effect, the request to play a sound. We learned earlier that reify is to make real. We need a little structure that stores the details of a pending request so we can keep it around until later. Okay, so we need, so they're using a struct play message, and I'm not really sure how structs in C++ are different than classes. Like, would that be the equivalent of just an object literal? So if I do something like this, const play message equals, and then just an object, and then we have the ID and the volume. Or is it more like gonna be like a factory that creates these? Next, we need to give audio some storage space to keep track of these pending play messages. Now, your algorithms professor might tell you to use some exciting data structure here, like a Fibonacci heap, or a skip list, or hell, at least a linked list. But in practice, the best way to store a bunch of homogeneous things is almost always a plain old array. Algorithm researchers get paid to publish analysis of novel data structures. They aren't exactly incentivized to stick to the basics. Okay, so no dynamic allocation in a simple array, no memory overhead for bookkeeping, information, or pointers, cache-friendly contiguous memory usage. For lots more on what being cache-friendly means, see the chapter on data locality, which I think is coming up. So let's do that. We have our class audio here. We have what's available publicly, doesn't really matter. We have an init function. So let's go ahead and add that in. We have an init method that is going to set this dot num pending is equal to 0. And in private, we set max pending, so we're going to need a constructor to set that. And I think with Webpack you can do things like just like set numbers, like num pending equals 0. But I don't think you could do that by default yet. But I haven't really been paying attention to like the latest changes in JavaScript. Okay, so here we're gonna have this dot max pending equals 16. We're also gonna have this pending, this dot pending is an array. Oh, of like the max pending amount. I think new array. The array length would be this dot max pending. And I think that will create us an array of undefined. And then we have the num pending, which is here. So to like get that in, we'll just call this dot init. We can tune the array size to cover our worst case. To play a sound, we simply slot a new message in there at the end. So in play sound, we have the sound ID, we have the volume, assert. Okay, so we need to make sure that the num pending, right, because this is gonna be like our index essentially into this array, is less than max pending. So we'll want to, assert is essentially gonna crash the program. We want to like quit out. So we want to do if this dot num pending is greater than or equal to this dot max pending, then I want to throw new error, and the message is going to be audio stack overflow. It's always fun when we implement our own stack overflows. That will immediately crash the system unless we handle that error with whoever is playing the sound. So that may be what we want. Let's see. Okay, so then we have our pending. Okay, so we're going to pending and put into the ID. So, oh, probably just greater than, because it sounds like we put in based upon what this is right here. So this can be this dot pending of position, this dot num pending. Then you have dot ID. This is just an array. There's no object inside of there, unless we're talking about this, like the play message, the struct play message. If we put those inside of this array, then we can definitely do that. But I can't access like ID off of that right now. So I need to put in, let's see, start sound. What is this? Play sound. We're going to this depending of num. Oh, play sound assumes that that is in there right now. Oh no, we're just adding into the array, and then we're gonna num pending. Okay, I don't know. I'm confused about like how we're going to like get this in there. So this entire play message, we're gonna have to put this in here. Play message. So play sound. This time I'm heading equals play message. But we have to like set that up to begin with. So maybe because we don't have like a struct like this, let's make this into a class, and then we can use it in one line. So class. We could also make it a function. So a function create play message. This is going to take in the ID and the volume, and then it's going to return an object. So return an object. Whoa, nope, not whatever I did there. Too used to like the Mac keyboards, and I accidentally did one on a Windows, and that did not make it happy. And then I want you to close this here and semicolon. Okay, so then you should be surprised you didn't auto reconfigure when I did that. All right, so then this is going to be, we want the ID and the volume to be used here. Okay, so now we can create play message right here. So this dot pending equals create play message, and then we're going to hand it the ID and the volume. And then that then enqueues this message up. And so that sets our ID and it sets our volume. And now we have our num pending plus plus. So whereas that, we don't have this start sound happen anymore. We don't have to like find this channel. All we're doing is creating this pending, and then this dot num pending plus equals to 1. This let's play sound returns almost instantly, but we do still have to play the sound, of course. That code needs to go somewhere, and that somewhere is an update method. Okay, so now we're going to have an update method on audio. And so we're going to loop through the sub-array of pending. So, I mean, there's a couple ways that we can do this, I suppose. I could do this like manual for loop. I think I can also slice off, and I think that would be fine because I'm just getting references to objects here, and that's like really, I don't think that affects. Let's try this. If I do this dot pending dot slice, will you show me? Let's see. Returns a section of an array, but I don't think it. Yeah, I don't think this this will affect the original array. It's not like splice. The original array should remain there. So what I can do is this dot pending dot slice. We're going to start from 0, and we're going to go to this dot num pending, and this is exclude. I don't remember if it's inclusive or exclusive. And then we can for each this to get an audio, sort of like whatever this audio play message is. So we can do a play message. And inside of here, we're going to do all these things where we find let's do this. Just stop play. That slice there. That for each here. In play message, we're now going to get the resource. So const resource equals, what do we call this? This is find, load sound. Load sound, and it's the ID, so we can do this on play message dot ID. We can do const, our channel is going to be find open channel if our channel is equal to -1, and just a quick early return. And then finally, we're going to start sound. So call start sound, and we're going to pass it in the resource, the channel, and then the volume, which is going to be the play message dot volume. And after we play all these, we need to remember to reset num pending to 0. So this dot num pending equals 0. As the name implies, this is the update method pattern. Let me see if I could take a look at whatever that message that came in was. Nope, nothing super important right now. Okay, so now we need to call that from somewhere convenient. What convenient means depends on your game. It may mean pulling it from the main game loop or from a dedicated audio thread. This works fine, but it does presume we can process every sound request into a single call to update. If you're doing something like processing a request asynchronously after its sound resource is loaded, that won't work. For update to work on one request at a time, it needs to be able to pull requests out of the buffer while leaving the rest. In other words, we need an actual queue. A ring buffer. There are a bunch of ways to implement queues, but my favorite is called a ring buffer. It preserves everything that's great about arrays while letting us incrementally remove items from the front of the queue. Now I know what you're thinking. If we remove items from the beginning of the array, we don't have to shift all the remaining items over. Isn't that slow? This is why they made us learn linked lists. You can remove nodes from them without having to shift things around. Well, it turns out you can implement a queue without any shifting in an array too. I'll walk you through it, but first let's get precise in some terms. The head of the queue is where requests are read from. The head is the oldest pending request. The tail is the other end. It's a slot in the array where the next enqueued request will be written. Note that it's just past the end of the queue. You can think of it as a half open range, if that helps. Since playSound appends new requests at the end of the array, the head starts at element 0 and the tail grows to the right. Let's code that up. First, we'll tweak our fields a bit to make these two markers explicit in the class. So we have our class audio. We have our init function, and now we're going to have to store head and tail. So this dot head equals 0. This dot tail equals 0. The way he wrote methods here makes it look like these are methods, but I don't think that's right. In the implementation of playSound, num pending has been replaced with tail, but otherwise it's the same. Okay, in the implementation of playSound, num pending has been replaced with tail. So we have num pending here. Nope, just playSound up here too. So this dot tail. Otherwise, it's the same. Okay, so we show assert tail is less than max pending. Okay, pending tail.id. So then we loop. Oh, I did it too many places. I was supposed to only do it in playSound. I also did an update by accident. Let's undo that really quickly. Let's just do it here in playSound. Okay, so this dot tail. There we go. So now we're going to enqueue it into our system. And we're only checking like the end of it. So we're adding it to the end and we're increasing. The more interesting change is in update. So an update, if head is equal to tail, there are no requests. Do nothing. Okay, so here is if this dot head is equal to this dot tail, return. We get our resource. Well, so first of all, I was right, because we're no longer looping through everything. We don't need this entire for each anymore. So we're gonna end that. We're gonna do that. We're gonna do that. Okay, so we're gonna grab our resource, load sound, and this is now gonna have to be this dot pending of position this dot head dot ID. Then we find the open channel. If the channel is -1, we return start sound. We pass it in the resource, the channel, and the volume. So this is going to be the exact same thing here. So this will be this dot pending of position this dot head dot volume. And then instead of this dot num pending being equal to 0, we head plus plus. So this dot head plus equals to 1. Right, because we just did we just went through the head, so now we can like increase 1. So we've removed that array to, I guess, the left. I forget that I'm mirrored sometimes. We process the request at the head and then discard it by advancing the head pointer to the right. We detect an empty queue by seeing if there's any distance between the head and the tail. This is why we made the tail one past the last item. It means that the queue will be empty if the head and the tail are the same index. Now we've got a queue we can add to the end and remove from the front. There's an obvious problem though. As we run request to the queue, the head and tail keep crawling to the right. Eventually, tail hits the end of the array and party time is over. This is where it gets clever. Do you want party time to be over? No, you do not. All right, so then we have head and tail, and then all the available stuff, of course. Notice that while the tail is creeping forward, the head is too. That means we've got array elements at the beginning of the array that aren't being used anymore. So what we do is wrap the tail back around to the beginning of the array when it runs off the end. That's why it's called a ring buffer. It acts like a circular array of cells. Implementing that is remarkably easy. When we enqueue an item, we just need to make sure the tail wraps around to the beginning of the array when it reaches the end. Which means that we're not going to throw this error anymore, I don't think. Because now we're going to say, okay, so if this dot tail is now greater than this dot max pending, we can now set assert tail plus 1. Yeah, so like if whatever the next one is modulus of max pending is not equal to head. Wait a second. Okay, so let's say this is like this. So 0, 1, 2, 3, 4, 5, 6, 7. Maybe we should do 6 to make an even number. So if it's 6 right here, modulus max pending, which I think is 10 or so. So that would be 1.2, I think. So it would be 2 on the, this result would be 2. If that's not equal to the head. Oh, if the tail, okay, hold on, I was mistaking this. If the tail plus 1, so this would be 4, modulus like 10, let's say, that would be 2.2, so 2 essentially. If that's not equal to the head, which is not there, I guess I don't fully understand this. Let's see. It's my greatest weakness, math. Replacing tail plus plus with an increment modulo that array size wraps the tail back around. The other change is the assertion. We need to ensure the queue doesn't overflow. As long as there are fewer than max pending requests in the queue, there will be a little gap of unused cells between the head and the tail. If the queue fills up, those will be gone, and like some weird backwards Ouroboros, the tail will not collide with the head and start overwriting it. The assertion ensures that this doesn't happen. So position of where we are, plus 1. Modulus max pending. Let's see if we can run that. So if I'm at position 4, or we have right here, we're at position 3. So we're at position 3, and obviously that's like then a plus 1. And then we want to modulus this with max pending, which is so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 is 4. So 0, 1, 2, 3, 4 would be like this position where it is. Head is significantly higher than that, so we're fine. But let's say tail was right here. That would be 0, 1, 2, 3, 4, 5, 6. So this would be 6 plus 1. Modulus 12 would be 7, which is exactly it's the next position over. I'm guessing, like, why couldn't I just check to see if tail plus 1 is not head? Oh, it's because we might be over here. Okay, so this is the reason. If we're in 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So if we're in position 11, this will give us this index. Because we don't want to check this, we need to check this index over here. So that's the reason why. Okay. Understood. So where is this? This is in play sound. If this dot tail plus 1. So if we increase this, and then we modulos with max pending, and if that is equal to this dot tail, so this is going to be this dot head. No, it's the opposite. This dot tail, this dot head. so if we've reached the end, then we can just return. Or no, this is still like a Stack Overflow situation. So if we're here now, there's nothing more that we can do. So we're going to return new error, audio queue Stack Overflow. I guess audio, it's not Stack Overflow, it's a queue overflow, audio queue overflow. Meanwhile, then, okay, so pending this dot tail, and then we create our message, and then this dot tail plus equals to 1. Now what's interesting is +1 modulus max pending, which we found out is essentially just whatever we put in. So if we modulus whatever this number is on the left, it gives us that number or 0 if it goes over it. So it's going to be tail is now going to be equal to this dot tail +1 modulus this dot max pending. Replacing tail ++ with an increment modulo the array size wraps the tail back around. The other change is the assertion. We need to ensure the queue doesn't overflow. As long as there are fewer than max pending requests in the queue, there will be a little gap of unused cells between the head and tail. If the queue fills up, those will be gone, and like some weird backwards Ouroboros, the tail will collide with the head and start overwriting it. The assertion ensures that this doesn't happen. In update, we wrap the head around too. So in update, we have if the head is equal to this tail, we return. We do this entire resource load sound pending this dot head dot id. We find our channel, we do all this stuff exactly the same, but now we're gonna do this dot head equals this dot head +1 modulus this dot max pending. There you go. A queue with no dynamic allocation, no copying elements around, and the cache friendliness of a simple array. If the maximum complexity bugs you, then you can use a growable array. When the queue gets full, allocate a new array, twice the size of the current array or some other multiple, and then copy the items over. Even though you copy when the array grows, and queuing an item still has constant and more amortized complexity. I don't know what like amortized means in this specific context. I can guess, but and queuing item still has a yeah. So it's because then you have to like potentially reallocate and move everything else over into like a new array, and that kind of sucks. We can use a vector, but then we're gonna have like we don't have that entire contiguous memory potentially. Aggregating requests. Now that we've got a queue in place, we can move on to other problems. The first is that multiple requests to play the same sound end up too loud. Since we know which requests are waiting to be processed, now all we need to do is merge a request if it matches an already pending one. Interesting, okay. So we have play sound, walk the pending requests. So go from, interesting. So, oh, right. We need to go through all the requests. If the IDs are the same, use the larger of the two volumes. So pending volume equals max volume, pending i.volume. Okay, so, and we don't need to enqueue. Okay, so before we add to the queue, we want to find out if it's already in here. So if this tail, okay, so we're gonna still do our check here, but now we need, before we just like add this in blindly, we need to find out if there's if the sound is already in here. So we need to loop through, but unfortunately our simple, like what we had before doesn't work anymore. Our audio play sound is unfortunately going to give us, so we need to, for I equals head, I is less than tail. I can't just do like an index of or anything like that because it may have been something that was played previously that we don't want to catch in this case. So we're going to do this for loop. So let index equals this dot head. So we're going to start at the head. Index, if the index is not equal to this dot tail, so as long as we're not equal to the tail, and then finally, index is equal to, right, index plus 1 modulus this dot max pending. A fun loop if there ever was one. So it's doing I++, but we need to sort of like reach the end of that, and then wrap around to the beginning. So that helps with that that logic. We could also use a while loop and then just sort of reset ourselves at the end of that. If pending of I, okay, so then we're gonna check the IDs. So if this dot pending of position index dot ID is equal to ID, then we want to make sure that the pending volume to set it to whichever one is larger. So use the larger of the two volumes. So this dot pending of position index dot volume is equal to, now they have max here. I don't think we have something like this in JavaScript, so we'll need to use a ternary. And then we'll just say volume is greater than this dot pending of index. Wait, they're math.max? Ooh. Okay, hold on. I haven't used that. Thank you, ZXSAP. That would be great to use. Okay, so math.max returns the larger of a set of supplied numeric expressions, and it looks like this needs to be an array of numbers. Awesome. Thank you so much for that. So then this is going to be volume and this dot pending index dot volume. It's a mouthful. So if we do this, we set the volume to be this, and then we also return at this point because we're done. Not an array. I thought I saw that that makes it look like it needs an array. Or is that showing that it's a spread from an array? Oh my God, why would you do that? The documentation shouldn't be using spread like that. Unless that's just VS Code being fun. Okay, thank you for that. All right, so then we choose the maximum between volume and this dot pending index volume, and that goes into this volume, and then we do an early return. And then this still happens if we get through this chunk of code, then this still happens. When we get two requests to play the same sound, we collapse them to a single request for whichever is loudest. This aggregation is pretty rudimentary, but we could use the same idea to do more interesting batching. Note that we're merging when the request is enqueued, not when it's processed. That's easier in our queue so we don't waste slots on redundant requests that will end up being collapsed later. It's also similar to implement. It does, however, put the processing burden on the caller. A call to play sound will walk the entire queue before it returns, which could be slow if the queue is large. it may make more sense to aggregate in update instead. Another way to avoid the O(n) cost of scanning the queue is to use a different data structure. If we use a hash table keyed on the sound ID, then we can check for duplicates in constant time. There's something important to keep in mind here. The window of simultaneous requests that we can aggregate is only as big as the queue. If we process requests more quickly and the queue size stays small, then we'll have fewer opportunities to batch things together. Likewise, if processing lags behind and the queue gets full, we'll find more things to collapse. This pattern insulates the requester from knowing when the request gets processed, but when you treat the entire queue as a live data structure to be played with, then lag between making a request and processing it can visibly affect behavior. Make sure you're okay with that before you're doing this. Using an object instead of a queue might be really interesting. And I guess you might still want a queue for that. Or I guess like instead of an array of a queue, we use a hash table, which is an object in JavaScript. And then we can just go straight in by the ID. And then we just loop through the objects and delete them, freeing up resources as it goes along. Spanning threads. Finally, the most pernicious of problems. With our synchronous audio API, whenever thread called played sound was the thread that processed the request. That's often not what we want. On today's multi-core hardware, you need more than one thread if you want to get the most out of your chip. There are infinite ways to distribute code across threads, but a common strategy is to move each domain of the game into its own thread: audio, rendering, AI, etc. Straight line code only runs on a single core at a time. If you don't use threads, even if you do the asynchronous style programming that's in vogue, the best you'll do is keep one core busy, which is a fraction of your CPU's abilities. Server programmers compensate for that by splitting their application into multiple independent processes. That lets the OS run them concurrently on different cores. Games are almost always a single process, so a bit of threading really helps. We're in good shape to do that now that we have 3 critical pieces. The code for requesting a sound is decoupled from the code that plays it. We have a queue for marshalling between the two. The queue is encapsulated from the rest of the program. All that's left is to make the methods that modify the queue, play sound, and update thread safe. Normally, I'd whip up some concrete code to do that, but since this is a book about architecture, I don't want to get mired in the details of any specific API or locking mechanism. At a high level, all we need to do is ensure that the queue isn't modified concurrently. Since PlaySound does a very small amount of work, basically just assigning a few fields, it can lock without blocking processing for long. In Update, we went on something like a condition variable so we don't burn CPU cycles until there's a request to process. Design decisions. Many games use event queues as a key part of their communication structure, and you can spend a ton of time designing all sorts of complex routing and filtering for messages. But before you go off and build something like the Los Angeles telephone switchboard, I encourage you to start simple. Here's a few starter questions to consider. What goes in the queue? I've used event and message interchangeably so far because it doesn't matter. You get the same decoupling and aggregation abilities regardless of what you're stuffing in the queue, but there are some conceptual differences. If you queue events, an event or notification describes something that already happened, like monster died. You queue it so that other objects can respond to that event, sort of like an asynchronous observer pattern. You are likely to allow multiple listeners. Since the queue contains things that already happened, the sender probably doesn't care who receives it. From its perspective, the event is in the past and it's already forgotten. The scope of the queue tends to be broader. Event queues are often used to broadcast events to any and all interested parties. To allow maximum flexibility for which parties can be interested, these queues tend to be more globally visible. That would be like that observer pattern that they mentioned. If you queue messages, a message or request describes an action that we want to happen in the future, like play sound. You can think of this as an asynchronous API to a service. Another word for request is command, as in the command pattern, and queues can be used there too. You are more likely to have a single listener. In the example, the queued messages are requests specifically for the audio API to play a sound. If other random parts of the game engine started stealing messages off the queue, it wouldn't do much good. In fact, it would be very, very bad because when we take a message off the queue, we move to the next thing. I say more likely here because you can enqueue messages without caring which code processes it as long as it gets processed how you expect. In that case, you're doing something akin to a service locator. Who can read from the queue? In our example, the queue is encapsulated and only the audio class can read from it. In a user interface's event system, you can register listeners to your heart's content. You sometimes hear the terms single cast and broadcast to distinguish these, and both styles are useful. A single cast queue. This is the natural fit when a queue is part of a class's API. Like in our audio example, from the caller's perspective, they just see a play sound method they can call. The queue becomes an implementation detail of the reader. All the sender knows is that it sent a message. The queue is more encapsulated. All other things being equal, more encapsulation is usually better. You don't have to worry about contention between listeners. With multiple listeners, you have to decide if they all get every item broadcast, or if each item in the queue is parceled out to one listener, something more like a work queue. In either case, the listeners may end up doing redundant work or interfering with each other, and you have to think carefully about the behavior you want. With a single listener, that complexity disappears. So this is basically the audio listening to this queue versus audio and the player listening to the queue. The same queue. A broadcast queue. This is how most event systems work. If you have 10 listeners when an event comes in, all 10 of them see the event. Events can get dropped on the floor. A corollary to the previous point is that if you have 0 listeners, all 0 of them see the event. In most broadcast systems, if there are no listeners at the point in time that an event is processed, the event gets discarded. You may need to filter events. Broadcast queues are often widely visible to much of the program, and you can end up with a bunch of listeners. Multiply lots of events times lots of listeners, you end up with a ton of event handlers to invoke. To cut that down to size, most broadcast event systems let a listener winnow down the set of events they receive. For example, they may say they only want to receive mouse events or events within a certain region of the UI. A work queue. Like a broadcast queue, here you have multiple listeners too. The difference is that each item in the queue only goes to one of them. This is a common pattern for parceling out jobs to a pool of concurrently running threads. You have to schedule. Since an item only goes to one listener, the queue needs logic to figure out the best one to choose. This may be as simple as a round robin or random choice, or it could be some more complex prioritizing system. Who can write to the queue? This is the flip side of the previous design choice. This pattern works with all of the possible read-write configurations: one-to-one, one-many, many-to-one, or many-to-many. You sometimes hear fan-in to describe many-to-one communication systems and fan-out for one-to-many. And I think that's the shape of the fan, like that or that. So one, many down here. With one writer, this style is most similar to the synchronous observer pattern. You have one privileged object that generates events that others can then receive. You implicitly know where the event is coming from. Since there's only one object that can add to the queue, any listener can safely assume that's the sender. You usually allow multiple readers. You can have a one sender, one receiver queue, but that starts to feel less like a communication system this pattern is about, and more like a vanilla queue data structure. With multiple writers, this is how our audio engine example works. Since playSound is a public method, any part of the codebase can add a request to the queue. Global or central event buses work like this too. You have to be more careful of cycles. Since anything can potentially put something onto the queue, it's easier to accidentally enqueue something in the middle of handling an event. If you aren't careful, that may trigger a feedback loop. You'll likely want some reference to the sender and event itself. When a listener gets an event, it doesn't know who sent it, since it could be anyone. If that's something you need to know, you'll want to pack that into the event object so that the listener can use it. What is the lifetime of the objects in the queue? With a synchronous notification, execution doesn't return to the sender until all the receivers have finished processing the message. That means the message itself can safely live in a local variable on the stack. With a queue, the message outlives the call that enqueues it. If you're using a garbage collected language, you don't need to worry about this too much. Stuff the message in the queue and it will stick around in memory as long as it's needed. In C or C++, it's up to you to ensure the object lives long enough. Same with Rust too. Pass ownership. This is the traditional way to do things when managing memory manually. When a message gets queued, the queue claims it and the sender no longer owns it. When it gets processed, the receiver takes ownership and is responsible for deallocating it. That's what I would probably do in Rust, is just take ownership of it, and then at the end of that block, it just gets removed from memory. In C++, unique pointer with generic T gives you these exact semantics out of the box. Share ownership. These days, now that even C++ programmers are more comfortable with the garbage collection, shared ownership is more acceptable. With this, the message sticks around as long as anything has a reference to it and is automatically freed when forgotten. Likewise, the C++ type for this is shared pointer T. Well, I could do that, but then I'll probably have lifetime issues with Rust if I do that. I think the ownership is the best way to go at it. The queue owns it. Another option is to have messages always live on the queue. Instead of allocating the message itself, the sender requests a fresh one from the queue. The queue returns a reference to the message already in memory inside the queue, and the sender fills it in. When the message gets processed, the receiver refers to the same message in the queue. In other words, the backing store for the queue is an object pool. I think if I were to do that, I would end up that feels more like a global queue. It's just global to everything. It's gonna be all over the place, and it's handing out okay, here's your tell me what it is and I'll deal with it. But if I use an enum for each message, and that enum could have different things in it, so it could have a struct in some of the arms and maybe an array or an int in some of the other ones. That could be interesting. See also, I've mentioned this a few times already, but in many ways, this pattern is the asynchronous cousin to the well-known observer pattern, which is sort of I noticed that at the beginning. Like many patterns, event queues go by a number of aliases. One established term is message queue. It's usually referring to a higher level manifestation, where event queues are within an application. Message queues are usually used for communicating between them. Another term is publish subscribe, sometimes abbreviated to pub/sub. Like message queue, it usually refers to a larger distribution system, unlike the humble coding pattern we've focused on. A finite state machine, similar to the gang 4 state pattern, requires a stream of inputs. If you want to respond to those asynchronously, it makes sense to queue them. When you have a bunch of state machines sending messages to each other, each with a little queue of pending inputs called a mailbox, then you've reinvented the actor model of computation. The Go's programming language's built-in channel type is essentially an event or message queue. And I believe Rust has a channel type too, but I haven't really played around with it. So we might be able to use that. So that might be something to look into. And maybe I'll look at that tonight to see if that's something worth doing a stream tomorrow morning with it, or if I want to sort of just move on to the next chapter. Or I could implement this in Rust tomorrow, because there's no inheritance. This is definitely something we could do. So maybe that would be a good plan. But if we that's all things. Pay attention to Twitter tonight, and I'll send a message out of whether or not I'm going to be doing the Rust stuff, and then plan the stream based upon what I discover tonight. But with that, we are done with chapter 15, which is the event queue.